So just to have a big picture of how the class is organized, we have 14 chapters, 8 in heat and 6 in mass. This is the first one in heat transfer. Okay, and then the heat transfer and mass transfer mirror each other for the most part. So the map that you are seeing here is only for heat transfer, and we're going to have a similar one for mass transfer with one or two important changes, but mostly it'll mirror. So we have 8 chapters on heat transfer: 1, 2, 3, 4, 5, 6, 7, 8. It is nice to see how the chapters relate to each other. It always helps. So the first one is simply a transition from thermo, and it's going to basically talk about energy conservation that we are going to use to do some energy balance problems. So the contents of this chapter, as I said, it's basically transition from thermodynamics, talk just a little bit about temperature sensing and what is the context of our study of this temperature change. How much changes happen in biomedical, how much happens in the environment. So as I said, we're transitioning from thermodynamics. So let's review two of the critical concepts from thermodynamics that we'll use all the time. One is the first law of thermodynamics that says energy is conserved, uh, that we're going to use in every chapter of heat transfer. And then the second law says heat moves from higher to lower temperature. That also would be understood throughout the heat transfer chapters. The point to make as we are transitioning is this information, as critical as they are, these laws do not tell us how fast or slow or what type of energy transfer we are having. So in this chapter, we're going to sort of recap and get comfortable with the energy conservation principle. But as I already said in previous slide, that it's not going to be enough to do all our problems. So we need some additional information that is pushed on to chapter 2 that has to do with modes of heat transfer. So here we try to use the first law of thermodynamics or the energy conservation principle. To use this, we really have to define some system boundary. So we have a system, and then we have the surroundings. And the system interacts with the surroundings through this boundary. And this boundary is very critical, because without that we cannot talk about what is coming into the system, what is leaving the system, how much of energy is generated, and so on. And so the conservation principle simply says that what is coming in minus what is going out plus what is generated should be equal to the change in storage of the system that's within this boundary. So how much is the change in storage is given by this. Now this is kind of a very general concept. It is not specific to heat transfer. It's not specific to thermo. To give you to make a point, I had one of my ex-students once stop by and said, yeah, we use this principle all the time in banking. Money in minus money out plus money generated is equal to change in the amount of money stored. So this is a very general principle. I want you to see we're using this concept in the context of energy, but the principle is even more general than that. To use the conservation principle, to apply conservation principles to that word equation, in minus out plus generation equal to change of storage, we're going to do a very, very simple problem. So the problem simply says that a solid of mass 5 grams at minus 10 and of specific heat so much is dropped into a it's a liquid which happens to be water at 10 degrees, and the water mass is this. What is my final temperature? So this kind of thing we do in high school, but here we try to recap, number one, and number two is we try to do a more methodical way and relating it to the word equation. Okay, so now we're going to basically do uh, the energy conservation problem, and in that process we're going to use the word equation, in minus out plus generation equal to change in storage. So first we define the system boundary. I happen to define the system boundary that is pretty much the boundary of a body 2, whereas body 1 is outside the boundary. What we will do now is we will go through and calculate each one of these terms. So first, recap, the thermal energy content of a mass m is mCp times T minus T ref. And then I already said that the boundaries have been defined this way. It happens to be the boundary of body 2. So since body 1 is outside, then the energy that comes into the system is whatever is the energy of body 1, which is its mass times its specific heat times T1 minus T ref. Next is out. Now the boundaries as I have defined, and it's given in the problem that there is no heat loss. So the system does not exchange any heat with the surroundings. So this boundary is kind of insulated boundary. This is given in the problem. So then the heat loss would be 0. So heat out would be 0. And this is a simple system where a solid is just going into another liquid. There's no chemical reaction, nothing else is going on, so there is no energy generation. And finally, we need to calculate the change in storage. So change in storage, so change is always final minus initial. Okay, so at the end of the process, when this goes in, and then we give it enough time, let's say the final temperature is T. So at that point, the final energy content is M1 Cp1 times T minus T ref. That's the energy content of body 1 at the final point, and likewise M2 Cp2 T minus T ref is also the amount of energy at the final state. Notice I use the same T because if you leave them together for a long time, they're going to reach an equilibrium and they will have the same temperature. So this part is my final amount of energy in this control volume. How much is the initial uh, amount of energy in this control volume? In this volume or the domain or the system, I'm going to use them interchangeably in this case. So in this, there was only body 2. So the amount of energy that was there initially is M2 CP2 times its temperature T2 initially minus Tref. So now we have all 4 terms. We simply plug into this equation. This is one equation and we have one unknown. So T is my unknown. So one equation we can solve for T as unknown. So notice again, this is my in, this is out generation, and this is the change in storage. So from this I can calculate T to be 3.33, and that, at least there's no reason that it is wrong, because if you mix, if you put two bodies together, one at -10 and one at 10, then the final temperature has to be in between these two, which it is. You also notice that this T is kind of a, you can say, a mixed mean temperature. A temperature, the final temperature is weighted by the capacity. Okay? If one is very big, so one is big or has a very large mass, then this term, the first term, would be, this one would be so much bigger than this. So we can ignore the second one in reference to the first, and so the temperature is going to be M1 CP1 T1 over M1 CP1, which is T1. Does that make sense? If this body is so big, it's got so much mass, then when it is brought in contact with 2 and you leave it for enough time, then the final temperature will be this temperature. So this formula, the way we have the final temperature, it kind of makes sense. Most importantly, this temperature came, the final temperature came by simply doing energy balance, and energy balance is simply a statement of conservation of energy, and this is the word equation for it. Now it is important to see that the choice of domain or choice of the system boundary is arbitrary, and that doesn't change the final answer. To make the point, here I chose the domain that includes both 1 and 2. So both of them are both 1 and 2 are inside the domain, and so we're going to redo the same problem and try to use the word equation in minus out plus generation equal to change in storage. Okay, so let's do the in term now. In is 0 because everything is already inside the system, so there is no more energy coming in. Now the out term is also 0 because it's insulated. The generation term is also 0 because it is not having any chemical reaction, or there's nothing complicated going on. So change in storage is equal to final energy content minus initial. Okay? So what is my final energy when they are brought in contact together and left for a long time? Then it will reach one final temperature, T. T is the final temperature, like we did before. So then the final amount of energy is M1 CP1 T minus T ref plus M2 CP2 times T minus T ref minus so this is the final, minus initial. So initially, how much was there? There were two bodies here. So M1 had a temperature of C1, T1. So M1 had this much energy plus M2 had this much energy. This should be negative, or we can put this whole thing inside a bracket. So this was my initial, and this is my final. So if I plug these four terms together, we actually get exactly the same equation, just that one term, the in term, has been transposed to the right hand side, but it is algebraically the exact same equation. So the choice of how we choose boundary does not affect the answer, and it shouldn't. And here we do just a little different version of the problem, just a little more complex. So let's say the solid we are dumping is not just any solid, but ice. So some of the ice is going to melt. So latent heat would need to be considered. Okay, so how does that change things? So going back to the first time we did the energy conservation, we got almost this equation. The in term and the final term had this, and a final minus initial. So in term is this, and this is my change in storage. So everything same except one difference. So suppose all the solid melts, then in the final content it has this additional amount of energy. M1 the mass that melts, and L is the latent heat. So let's see, M1's unit is kg, and this is in kilojoules per kg. So if they cancel, then this is some amount of energy in joules that has to be considered, because the water has this additional amount of heat. So then again, it's one equation, and the only unknown is this T, and so we can solve for T. But of course the answer is going to be different because we have the latent heat. Then the other part gets a little more interesting, is not all the ice melts, but part of the ice melts. So this is only possible thermodynamically if the final temperature T is no. This is only possible thermodynamically when you have an ice water system that is in equilibrium, and that means we know the final temperature. It has to be 0 degrees. So the unknown here in the same equation that we used from before, T is known because the final temperature can only be 0. If ice and water has to coexist, the final temperature has to be 0. But the amount that would melt to lower the temperature, or to lower the system temperature to this temperature of 0 degrees, that is my unknown. So here we will solve the same equation for M1 star. Okay, so let's make some observations from the two problems that we did, two or three versions of a problem. Thermo deals with the end or the equilibrium state. We were able to calculate the final temperature. That we were able to do using thermo. Now there are two questions. In the energy conservation problem that we did we concern ourselves with the mode of energy transfer? As we put the solid and the liquid together, did we talk about conduction, convection, radiation? That's the first question. And the second question is, do we know how long does it take for the process? When does it get done equilibrating the temperature? So at this point, pause the video and for about 2-3 minutes and think of the answers to these questions, and then come back to the video. So for now, the answer to the first one is that we did not concern. So that's the power of thermodynamics, that it does not matter what the modes are, it can tell you what the final result is going to be. That's the power. The second one, which is a limitation of the thermodynamics, remember we had no clue on how long does it take for the heat transfer process. 1 minute, 1 day, forever. We have no idea about that. It is this limitation that leads into the course for heat transfer, where we have a much better idea as to how long does it take for the process. So to do that, though, we need additional laws. So the point of the exercise and this slide is we need more information. Just energy balance is not enough. This will happen in chapter 2. So moving on to the next part of the contents of this chapter, we will talk about temperature sensing a little. Normally temperature sensing can be a course by itself. That's not the purpose here. I want to have some relevance to these temperatures that we are talking about all the time, and how we get to those temperatures, how we get to know measuring, how we get to have a number for those temperatures. Okay, so this is the only slide that we have, and it's just trying to relate to everyday things. So for example, most of you have seen a thermometer like that, and the basis for that is that the liquid in red, which is typically an alcohol, it expands with temperature. So if you calibrate the expansion with temperature, then by knowing how far it has expanded, you can say what the temperature is. And so likewise, this being a mechanical process, you can have electrical process. So for example, this is the property of a bimetallic junction, that when you have two dissimilar metals and you kind of join them on one end, then a voltage is created at the other end. And this voltage depends on the temperature at the thermocouple junction. So if you measure the voltage, versus temperature, then again you have a calibration curve from which, by measuring the voltage using a voltage meter like a multimeter or voltmeter, you can get back to temperature. What is the main point? The main point is temperature is measured by converting the temperature effect into some other physical effect that we can measure. So in this case, temperature was related to expansion. In this case, temperature was related to voltage, to quantities that we can measure. So that is the basic idea of temperature measurement, by relating temperature to some quantities that we can measure. Related to measurement, again, there are 2 points that I want to make that is extremely important in the context of biological heat transfer. One is of course, there is a lot of variability. So this is a body temperature measured at 5 different sites, and whereas this is the average, you have quite a bit of variability in the measurement. This is inherent in a biological process. The other point is that the variability is what? Here it's 1.5 degrees. So it's not like tens, hundreds of degrees. It's a small amount, but small amounts are very small amounts of variation has a lot of implication. So it's very important to see in bioheat transfer that we're talking about small variations in temperatures that can make a huge impact. Okay, so how do humans sense temperature? So the way we sense temperature is we have nerve endings that are receptors under the skin. And these nerve endings send signals of varying intensity. So for example, this is the cold receptor. So over this range of temperature, depending on the temperature, it sends so many impulses per second. So like that, we have heat receptor, again nerve endings, and then we have pain receptors. Okay, and so it is the number of impulses that relate to the temperature, and that's how the temperature is sensed. The other point is, and that's again brings in biological complication, these receptors adapt rapidly. A good example is when we jump into the swimming pool, it may feel very cold at the moment we jump in, but after a few minutes, it does not feel as cold. So these receptors that send out impulses, they adjust. A few points about how do plants sense temperature. After we talked about how do we sense temperature, how do plants do the same? So temperature increase or decrease affects a number of things: the membrane fluidity, the protein conformation, then other structural changes, and then enzymatic activities. All these are affected by temperature, and that is how the plant senses temperature. For example, when temperature lowers, membrane lipids become more unsaturated, and that makes the membrane more fluid, that sets up new reactions. So these cold stable microtubules are synthesized, new reaction, and then that sets up a new enzymatic equilibrium, and in the new equilibrium, then the temperature sensing is switched off. So the last section of this chapter has some just general comments, just a sort of a overview of what is the context of temperature changes, how many degrees are we talking about, and so on. And this, by the way, is where I normally teach the course in Ithaca, New York. And this is the temperature. One of the winter days, it's -8 in Fahrenheit. Okay, so in the context of biological systems, uh, how many degrees of variation are we talking about that can make a difference? So living systems tolerate only a narrow range of temperature. So here you have everything from man to chicken to housefly, and the shaded region is the region where the particular system can tolerate temperatures and still have a normal life, and that is a very narrow range, very narrow range. And then the other point is most biological activity ceases below 0 degrees. So below 0 degrees, as soon as it starts to form ice, for example, most biological activity ceases. Temperature ranges for bacterial growth. You might be interested, the two common ones, the psychrophiles, lower temperature bacteria, the refrigerator bacteria, and the bacteria that we try to destroy when we process canned foods, that's at higher temperature. So again, in both cases, you do see actually in this case a relatively higher range in which they survive. Now that doesn't mean they're equally active in terms of growth, not at all, but at least they survive within a fairly large range. And still, even when it's fairly large, you're still talking 30 degrees, 35 degrees, not more than that. Temperature range for normal human body is very small. The core temperature varies no more than 2 degrees. Any more than that can be quite disastrous. So the deep body temperature is about 98.6, where by the time you get to even 1.5 degrees higher, then sweating begins, and 2 degrees lower, then shivering begins. And then you get to progressively more difficult conditions either way. Okay, so we're talking very narrow range of temperature. Now, one number that would be quite useful for this class is locally, not the core temperature, but when you're trying to destroy tissue, like in a cryosurgery, or we want to look at skin burns. Well, how does that? So those tissue are destroyed at this kind of temperature range. So at the higher end, 43 to 45 is the range that we need to reach to destroy tissue, or tissue gets destroyed if it reaches this temperature. Then in the lower range, if we want to be totally sure in cryosurgery, for example, that the tissue has been destroyed, then we need to reach something like -45°C. So these two temperatures are going to be useful in some of our applications. Finally, in the context of the environment, of our environment, a few degrees there also can be catastrophic. So sea levels can rise, up to 1.5 meters for just few degrees change in temperature. So if we look at data over the years, let's say for the last 150 years or so, then the temperature change is well correlated with CO2 change this way, okay? But the point to make is the temperature change, the warming so far is only about 0.5 degrees, and that is worrisome. So the point to make is very, very small changes in temperatures are going to be extremely important in the context of the environment. So to summarize then, thermodynamics tells us how much energy is going to be transferred, which way it goes from hot to cold, but not at what rate, not how long it will take. So energy content of a mass is given by mCp T minus Tref, right? Then the first law says energy is conserved. And from that, we write our energy conservation equation. This is the most useful thing that we will have from this chapter that we are going to use for every single one of the 8 chapters on heat transfer. So most important, this one, in minus out plus generation equal to change in storage. Second law says heat spontaneously flows from higher to lower temperature. And in all this process, what is missing is the rate of energy transfer. How long does it take? That's what we will do in chapter 2.